This is an example of a test of joint significance. And rather than looking at the output, I'm just going to talk about the meaning behind it and how it's working. So let's suppose we have a model with three independent variables. And let's say after we run the regression, we find that, say, these two in a t-test were insignificant. So what we're wondering is, are they actually contributing to the explanation of why, but we can't detect it individually? So in a test of joint significance, this would be the unrestricted model. We already estimated that regression, but let's think about the restriction. So if those two don't matter, then what that would imply is basically both of their slopes are already 0. So this model would be just as good as the model with both of them included. So when we're putting together our null hypothesis, what we're testing is, are they both 0? And so this is two restrictions. And our alternative in this case is at least one is non-zero. So it doesn't require that both of these slopes are non-zero. It just requires, when we reject the null, that one of them is non-zero. And it can be that it's non-zero and we have not been able to detect it in the unrestricted model because the coefficients are potentially interfering with each other. Remember, in a multiple regression model, all the coefficients, their own standard errors depend on what's going on with the standard errors of all the other coefficients as well. So this would be our null and alternative. And let's suppose I set a 5% level of significance. Then if we want to use the R-squared form of this regression, or of this test statistic, then what we need to use is an f-test that looks like this. We're going to use R squared from the unrestricted model minus R squared from the restricted model. I guess I should be using lowercase r's to make it more clear. And this is divided by Q, where Q is the number of restrictions. And then the overall denominator is 1 minus the R squared of the unrestricted model divided by n minus k minus 1. So we have two models, and if we want to estimate this without some special package in R, we can just run two separate regressions. We take the R squared from the unrestricted and the R squared from the restricted, divided by 2, unrestricted again. This n is our sample size, of course, and this k is the number of variables in the unrestricted regression. So just keeping straight, k is 1, 2, 3 variables, and the reason we have an additional minus 1 is what we really use there is we're thinking about the number of parameters that were estimated. So just to clarify that for a minute. Okay, so that's how we're finding the f-test. And let's think about f-critical, because we didn't talk a lot about the f-distribution itself. So it's a distribution based on squared things. If we think about the r-squareds, they're all squared. So it's always positive and skewed right. Our f-test is always a one-tail, right-tail test. So alpha equals 5% would be here. The rejection region is always coming from the critical value, so it starts with F critical. And then after our F test has been computed, similarly, we would have a decision that if F test falls in here, we do not reject, and if it falls to the right of F critical, we would reject. So let's go back to F critical for a minute. It always has a numerator degrees of freedom and a denominator degrees of freedom. It has two. So let's think about where these are coming from. If you can hear a cat purring, I can't get rid of him. So numerator degrees of freedom is Q, and think about that's the numerator of what we're testing. And the denominator degrees of freedom is n minus k minus 1, which comes from here. So thinking about the degrees of freedom that way helps us see that our critical value is adjusted for precisely the number of restrictions and sample size that we've been using. So then, to form our conclusion, let's think carefully about how we state our conclusion. If our p-value is smaller than alpha, let's put p-value in the picture. So let's suppose our f-test landed here. And just a reminder, the p-value is what's associated with the area or the probability that goes with a test statistic, and alpha is always the probability that goes with a critical value. So let's suppose it fits like my picture, that the p-value is less than alpha. Then our conclusion would be reject the null at a 5% level of significance, which would then imply that yes, we have shown at least one of those, one of the variables x2 or x3 or both are significant in explaining variation in y. If we had do not reject, then we would say we have not shown that at least one of those are significant in explaining variation in y.